Heteronuclear molecular orbital diagrams are going to look a little bit different, although fairly similar to the homonuclear diatomic diagrams. In order to really show you this contrast, what I want to do is show you two different molecular orbital diagrams, one for diatomic nitrogen and one for nitric oxide. All right, so what we'll need for these is the atomic orbital electronic configuration for each of these atoms. So you know for nitrogen it's 1s2, 2s2, 2p3, and for oxygen it's 1s2, 2s2, 2s2, 2p4. All right, now as we noted in the previous video, the effective nuclear charge on the oxygen is greater than it is on the nitrogen, which means that its energies will tend to be lower. So the energy of oxygen will be less than the energy of nitrogen for comparable orbitals. So when I draw these diagrams, and I'll position the N2 one first, I'll have my 3p orbitals, and they'll be, say, at this energy level. So I'll draw the same ones over here. And then the 2s orbitals for nitrogen, say, would be about here and here. There's nothing exact about these drawings here. I'm just drawing them approximately. And we know that the 2s, and I'm leaving out the core electrons in the 1s, that will form a sigma antibonding and sigma bonding orbitals here for N2. And we'll have 2 pi bonding orbitals, then a sigma bonding orbital, and then the anti-bonding orbitals corresponding to each of those up here. Okay, so this will be our molecular orbital setup for N2, and when we fill in the electrons for N2, so we'll have 2 electrons in each of the 2s orbitals, so these will all be full. So again, these are non-bonding orbitals down here. In the 2p case, following the Hund's rule, we'll have unpaired electrons in all of these. We'll have a total of 6 electrons, and they will end up filling all 3 of the bonding orbitals here for nitrogen. So as expected, nitrogen has a triple bond as indicated down here. All right, so very straightforward, no electrons in the antibonding orbitals. This is a pretty straightforward case, and it confirms something that we're all taught from earliest levels of general chemistry, that nitrogen has a triple bond. Okay, what happens now when we combine this with oxygen? Well, the oxygen energy levels are going to be lower for the atomic. So let's draw them down here a little bit. Okay, so here will be the oxygen 2p's relative to the nitrogen 2p's. The oxygen 2s will also be lower down here. So now when I draw the molecular orbitals, there will be one down here, the bonding orbital, that'll be a little bit closer in energy to the oxygen, and an antibonding orbital is a little bit closer to the nitrogen atomic orbital. Okay, for our case of the pi orbitals and the sigma orbital due to the 2p's, I don't actually know which one is lower in energy, but I'll continue to draw the pi orbitals as lower in energy. All right, but then the antibonding orbitals will again have this pattern. So we'll have this set up. And now when we insert our electrons in here, again, we'll each have 2 electrons in the 2s orbitals, so they'll fill these things. So once again, these will end up being something like non-bonding electrons that stay more or less in their atomic orbitals. And then we'll have the 3 electrons in the 2p orbital for nitrogen. We'll have 4 electrons in the 2p orbitals for oxygen. So we have a total of 7 electrons. We'll fill these 3 lower ones using 6 of the electrons, and we'll have 1 electron left over. All right, so not a huge difference, but it does make a difference in terms of the general results for our heteronuclear diatomic. Okay, so let's look at things. We've got bonding orbitals down here, and 1 antibonding orbital. So what does that mean? Our bond order for NO is going to be 1/2 of 6 bonding electrons minus 1 antibonding electron. Notice I haven't included any of these down here. I've treated those as non-bonding. They're going to cancel each other out when it comes to bond order anyway, so no need to include them. So I'll have 1/2 of 5, or 2.5. Now this is still a pretty strong bond. Stronger presumably than a double bond, okay, but it's not quite as strong as the N2 bond, so it's a little bit weaker than that. A second conclusion we can draw from this is we have one unpaired electron up here, so this should be a paramagnetic species. Okay, it doesn't have all of its electrons spin paired, and so it's going to have different magnetic properties from N2. Now, other things that we can do with an atomic molecular orbital diagram like this is imagine what life would be like if we, say, lost an electron. If we lose an electron from NO, what will we have? Well, this would be the electron that we would lose, this top one up here. And what we would be left with is an electronic configuration for the molecule that looks a lot like nitrogen. So in other words, this would result in a stronger bond for NO, presumably. All right, so NO plus has a stronger bond than NO. It would also be diamagnetic, so it would no longer have this paramagnetic quality that we have in the neutral molecule. What would happen if we added an electron? So then we would form NO minus. Well, does it have a stronger bond or a weaker bond? Well, we can't put the extra electron down here in the bonding orbitals. It would have to go up here. So our extra electron would end up being in this other pi orbital here. It would not spin pair with the first electron in the pi star orbital. So again, we would still have a paramagnetic molecule, actually a paramagnetic ion, but we would also have a weaker bond because we've just added another electron to an antibonding orbital. So our bond order would be 2. So I hope this gives you a little bit of a feel for how you might construct a heteronuclear diatomic molecular orbital diagram, but also some of the extra information you can get from it once you begin to populate that MO diagram with electrons.